EECS 281, lecture number 6, Arrays and Containers, spring 2020. Project 2 right around the corner here. We've got a release date in about an hour and a half. Just after lecture closes, it should go live. So while you're listening to this lecture and you're starting to prepare for Project 2, which gets released after this lecture, you can look at the standard priority queue. You're going to be using standard priority queue in the simulation portion of the project, and then you're going to be writing something similar to standard priority queue in the other half of the project. So work on building a standard priority queue, do something with an object, either a class or a struct inside, and a version of it that uses a functor, because if you use a non-built-in type, then you're going to need a functor to help the priority queue to determine which object it should pick as the most important. So using a functor and an object inside a priority queue is good practice for what you're going to be doing in Project 2. There are a couple of papers that we've submitted with this project as well. That's going to be one step of it as you implement the pairing heap. That's not a thing that we teach. We give it to you as the two academic papers. You read the papers and try to implement the container. And then there's also an STL card that's posted on Canvas. This is someone else's resource from the Jasudis textbook. It's just a very nice one-page summary of the algorithm library. So it's a list of them with a one-liner about each function so you can get familiar with it. So being very familiar with what's in there is important. You don't have to know all of the things that are in there, but if you're familiar with them, then you can know what to look for and when to go looking. Couple new job interview questions here. So you use these as brain teasers. Think about things. I like to use them when it's time to go to sleep. Try to figure out a more efficient way to do something like that. So the first one is, assume that you have an array that has a majority element. By majority, we mean greater than 50% of the elements in this container are this one particular element. Your goal then is to find which element it is, or what the value of the element that is greater than 50% of the elements in the array are. The limitations, however, are you need to get this done in linear time with only a constant amount of memory. This is fairly easy with linear time and linear memory, but when you reduce that to constant memory, you have to get a little bit tricky. Some problem solving. Oh. And there we have it. So the second job interview question, same sort of thing. We've got an array now that has an element that's in there more than a third of the times. Still trying to track down that element in linear time using a constant amount of memory. Well, maybe not a constant amount of memory, but it's not a linear amount of memory. Check these two things out after you wrestle with them for a while, see if you come up with something. If you don't, or if you do, you can verify it by checking out Moore's algorithm for the first one. And then the second one, you can find that by looking up the Misra-Greaves algorithm. Check both of those out. It's good stuff. Today we'll be talking about container classes, array-based containers in particular. So it's important that we understand how arrays work. Arrays in the end turn out to be syntactic sugar. We like to be able to write an array with square brackets and get some action in there. In reality, that's just syntactic sugar. That's an easy way to write things that the compiler interprets and then makes what actually happens go on there. So, what do you think here? I've got an array of doubles, A, and an int I, and then the C output statement. So the question is, what happens in line 5? Does it compile? If it does compile, does it have an error? Or does it compile and work? Think about that. Turns out, this works. As I mentioned, syntactic sugar, you see here that a square brackets I gets converted to dereference a plus the offset of I. So if I turn that around and say I square brackets A, it gets converted to dereference I plus an offset of A. And since addition is obviously commutative, A plus I is the same as I plus A, and these both output 2.2. Pretty crazy, I know. But that's what's going on when we're doing square brackets, right? I mentioned it being syntactic sugar. We get to write it like this or like this, and then what happens is this when the calculations go down. So that's what's going on as we get deeper into this. That's one of the things that when we look at, when we were step counting, I kind of waved my hands at the number of steps a thing took. So we said using an array with square brackets was one step, but clearly here we see that we would have had to do some addition and a dereference to get a value out of there or to get a value in there. So it would have been more than one step, but we also know that when those steps are a constant number of steps, so instead of just one access, maybe it's 2 calculations per access or 2 operations per access. That's a constant amount of work. It doesn't change with the number of items. So accessing an item in an array doesn't take me more steps when there are more items in the array. So it still remains constant. And then when those accesses are constant, we see that the only thing that was important, again, is just our loops. So as we look forward, we're going to be saying we need to understand how these C arrays work. That was what that last example was. We're getting inside some of the internals there. We need to understand how arrays work, how pointers work, how C strings work, all of these things at the C level, we should be able to understand them. We end up writing a lot of slide code in them and examples, and if you can do it in an interview or if you run into it in legacy code at work, it's important to know that stuff. But in 281, as we work on our projects, of course, we're going to avoid C-style arrays. Use a vector. That's a great way to go at it. If you want to, you can also use a deck. We see that decks have some improvements over vectors. Vectors have some improvements over decks. So it falls back to the 281 answer of it depends. If you're going to use something that's going to hold contiguous data, however, though, let's try to avoid C arrays. You could also use the STL array class, which is fairly limited in usage there. That one, because of the way that the template is declared, you have to know the size at compile time. So it's more restrictive again, similar to the C-style array. So we like the ability to be able to grow and not have to know things ahead of time. That's where vectors really help us there. But if you do have a particular operation where you know you're going to know the size at compile time, you could use an array. We're trying to avoid pointers. At the very least, use the containers whenever possible. When you can use the containers, then it makes function objects helpful. We can use integer indices instead of pointers oftentimes, or even iterators when we're going to work on the entire container. An iterator works really well there. And we'll see how iterators are actually faster than integer indices used as accessors through square brackets. So if we know we're going to parse an entire container in the STL, use an iterator. It's faster than square brackets. Using C++ string objects, of course, as opposed to using C-style strings. So these things are all going to speed up our coding because it's debugged and it's got some protections in some of these things. It's got all of our memory allocation and deallocation is automatically handled for us. So that's nice to be able to understand what's going on. It's even nicer to code quickly with solid, safe code. Just in a review of arrays in C/C++, you can see here that I've got this array R declared with some characters in it. This is a character array, which is similar to what a string is, but a character array doesn't necessarily need to be null terminated. However, if I want to treat a character array like the pointer it is and then say, well, I could just pass R to string functions, I can. And it will work up until the point where it gets to the end of the container and is looking for a null terminator. So if I do include a null terminator in my character array, it will behave just like a string. If I don't include a null terminator in my character array, it will behave just like a string, which means it's going to do all of its operations until it sees a null character. So if I don't add one, then I'm going to run right off the end of my memory segment there, possibly causing seg fault or corrupting other memory that I really care about. So be aware that when you're using C-style stuff, that you have to understand what you're doing. All right, so in this case, we can use square brackets access here. And if we remember from our earlier example, what we're really doing is something that looks like dereference R plus 0 and set that equal to E, right? And that would be changing this value right there. So we can read from it similarly using square brackets. Here is a reference to the fact that R, even though it was declared up here as an array, is really a pointer. And you see that we can set a character pointer equal to the value that is the character array, right? Because that R is a pointer, and remember, square brackets here on the end of that is just syntactic sugar for interacting with arrays like that. So here we can grab a particular item. I've set this character pointer equal to the address of the one index item. So now I've got a pointer here that's pointing at this value. You can see that. And if I were to sort of dereference character pointer as a string, it would try to print the string ECS. However, I still need a null terminator here, or bad things may happen. Good thing about arrays is we get random access in constant time. Index numbering always starts at 0, which is a problem when you start programming computers, but then it's a savior when you figure out how to do modular arithmetic, and the fact that zeros are a great place to start. They don't have bounds checking, and one of the primary issues with dealing with C-style arrays is you always have to have the length somewhere. Not so much in C-style strings, because even though they're functionally a C-style array, the C-style string has the implied null terminator. So the pointer is more than enough. If you just pass a C-style string pointer around, it knows that the size is going to be determined by some element that's going to tell you when to stop. That's not necessarily the case. So if I've got an array of integers, I might want to have a 0 in there, but not mean that 0 is the last one. So you always have to keep the size separately. Then when you pass an array as a member to a function, you have to pass the size along with that as well. So that can be a little challenging. C++, of course, gets around that in the containers that we're using. When we use a vector, the vector is actually 3 pointers, right? And from those 3 pointers, we can determine the total memory that's been allocated, the capacity. If we subtract the capacity pointer and we take that and subtract the base pointer, or we can also subtract the base pointer from the size pointer to tell you how many items are actually in there. So those are the 3 pointers. We've got a base, a size, and a capacity, and that'll be pointing to different places in the memory there. As we work on fixed size arrays, we can look at this example of using a 1D array and a 2D array. In this case, we're going to be storing 9 values in both different cases, and I'm going to see how I can sort of declare the memory in 1D format here. The array 1D is declared as square brackets 9, whereas here my array in 2D is declared as square brackets 3, square brackets 3. So this is 3 rows of 3 columns each, which is of course 9 elements. And so in memory, we kind of think of them as looking like this. But if we understand how memory works, it's actually just an increasing collection of addresses. So in reality, as I work my way through here, this address followed by this address followed by this address. The next address in memory is this address here, as I look at index 3, index 4, index 5, index 6 there. So down below that, you see we've got a couple of different conversion functions. If I want to go from rows and columns in this diagram to where it would be in just a one-dimensional there, I can use this function there, and vice versa. If I want to figure out what row and column this would be if this was two-dimensional, I can pick an item here and take its index mod by the number of columns, divide by the number of columns, and that will get me column and row. Another way to do 2D arrays, these 2D arrays that we're using here, these are fixed at compile time. You see that here in line 2, I said the array object, or this array that I'm declaring, this int array, has rows and columns in there. So this is then thought of as a 2-dimensional array. It's an array of arrays. However, I only have one pointer. I've got the one pointer to the base address of R, right? And then anytime I do some double square brackets access, the compiler is going to do the math for me. Because the compiler knows what's going on there when R is declared, and I say rows and columns. It looks at how R is declared, it knows what's going on there, and I square bracket something in here and multiplies that by 3 and adds it to this address, and so on. So we think of this as being a little bit safer. We're not using pointers. We have the pointer, obviously, R, that we use, but we don't have to use pointer access. We can still use square brackets access. The size is set at initialization, and it ends up using less memory than the pointer version, which we'll see in a minute. And it uses less memory because there's only one pointer, right? There's the one address. There's not even really a pointer. There's just the address of where things are. We keep track of that. So we do have the overhead of the address of where things are, but you're always going to have that overhead in any variable, knowing where it is, plus the data itself. G++ does have an extension which is non-standard across the board, so we still don't recommend using it, but that extension would allow you to declare arrays with variables. Modern C++ stuff. Here's the second way to do a 2D array. This is with double pointers. So if I look at the type of my previous declaration, where it was R, square brackets, rows, square brackets, columns, what I'm declaring there is really an int pointer. It's something that needs to be dereferenced. And then when you dereference the thing, you're going to go there and you're going to have to track down what's there. But this is one that's explicitly a 2-dimensional pointer, a pointer to integer, right? So when I dereference R, I'm going to be sort of getting myself this collection of pointers, and then I can pick one of those pointers and dereference it, and I can get to where my integers are. So that's what's going on here, and you can see that with the code as written, I'm able to use vectors. So this is the way that you would use C-style arrays with dynamic runtime sizing. Get your rows and columns, and then I'm going to use the new square brackets operator. Say new square brackets, I want an int pointer square brackets called rows, right? So what this is an array of int pointers, right? The square brackets from new square brackets says I want an array of these things. These things are of type here, int pointer, and the name of the array, is R, right? And I'm going to use this rows value to tell me how many things are in the array. All right, so this one uses double pointers. The good news about this is I can set my rows to be of different lengths if I want to. I can set this pointer here 0 to some container of size 3, and this pointer to a container of size 4, and this pointer to a container of size 1 if I like, because I'm not depending on this memory being contiguous. So you can see how this is going to be a little bit slower than this previous version, where I've got one pointer that comes in, and then these things are all contiguous in memory. This particular version, each row is contiguous in memory, but the rows are not necessarily contiguous. So in this case, you see that I've declared the initial set of pointers. This is giving me R, this 0, 1, 2. Then I've got to take this other set of new square brackets operators to set up where my actual ints go. This container holds int pointers. This container holds actual ints, right? So instead for each one of those things in R, I'm going to set that equal to a new square brackets collection of ints that are calls wide. So now I've got this 3x3 area for data, although it's not really 3x3. It holds 9 items, and it's 3 collections of 3 things. right? And I can run through the same sort of loop. And I can even use the same access method, right? The same syntactic sugar works here. I can say R square brackets, even though it was declared up here as an int pointer. That's okay. The compiler takes care of this for me and it's brilliant. But it is fundamentally something different here, right? Every time I've got to do an access, I've got to first get into this array, figure out which row I'm going into. Then I go to the row and figure out which column I'm going into. So there's 2 memory accesses there, not just one. That's another reason why it's slower. And the fact that it's not contiguous has me oftentimes jumping around memory a lot more than I would if I was just doing a 2D declaration. All right. Now to make sure that I clean up, though, it's very important. This is the part that we get saved by in the STL. All of our memory is handled for us. But up here, I've declared some new square brackets. I've done a new square brackets there again. So when I get done, I've got to unroll this by doing a delete square brackets for every one of the new square brackets I called. So the first thing I did was the outer. Then I went inside and looped to do the inners. So in reverse, I'm going to deallocate, right? So I'm going to loop to do the inners to delete square brackets, and I'm going to do the outer with the delete square brackets. And delete square brackets always has to be used when you use new square brackets because the compiler keeps track of the things that are there. When you say new thing, later on you go back and delete thing, it's a one object sort of deal. I get one of these, I can delete one of these. If you say new square brackets thing, you're saying give me some things. So give me 10 of these. The only way that delete is going to work is if delete knows how many there are. So that's why delete square brackets is distinct from delete, just because new square brackets is distinct from new. The compiler actually stores the size with the pointer there, and so prior to where the memory is, there's a value that tells the compiler how many things are there. So then delete square brackets can jump before the pointer, see how many things it should delete, and then delete them. So always use new with delete, of course, and then when you use new square brackets, make sure that you use delete square brackets as well. So when we've got fixed arrays, the pros and cons are pretty straightforward, right? These are allocated on the stack. When I put one in this format right here, right? You see that R here is declared and its memory is allocated inside the stack frame because I know at compile time how big it's going to be. So the compiler sets that up inside the stack frame. As well, since it's in the stack frame, it goes out of scope. It's automatically deallocated for me. So that's really nice. And then you can see that the square brackets operation, because the compiler knows the number of rows that are in there, the number of columns that are in there, it can do the multiplication to figure out how to do R square brackets I square brackets J in one memory allocation. Takes the base address, multiplies the columns by I, adds the columns in J, and then goes there in one access. The cons are for too big an N, right? Too many items, that makes too much room in my stack frame. So I've got a fairly limited size of fixed array that I can declare inside a function like that. Another con, of course, is it's fixed at compile time, and the overhead of trying to pass these as arguments to functions. You have to add every additional parameter that you're sending there. So if I'm going to send a 2D array, I have to send the number of rows as well as the size. And I'm going to add a 3D array. I've got to send the number of rows and the number of cols. And so they can be a little challenging there. One thing that we also want to do is, because they're fixed length, we want to be very careful with how we manage these things. This last caveat, this word to the wise here, is avoid fixed length buffers for variable length input. I don't know where the statistic comes from, but says this is a source of 70% of security breaches. We've got a fixed length buffer and variable length input. So at compile time, you said I needed, I don't know, somebody's name. Some names are longer than others. What if I just give myself 50 characters? That'll be safe. Well, some names are even longer than that. Let's say I've got 100 characters. So I'm going to read this name in there. Data goes in. Next person comes, More data comes in, next person comes, data comes in, next person comes. So we put data in this area, and then Bob shows up. Bob's got 100 characters to put his name in there, but his name's Bob, so he only uses 3 characters. What happens is those first 3 characters in the null terminator are written into that buffer of size 100, and the remaining 96 bytes are untouched, right, from the previous entry. So you can see how if information gets passed into a buffer and is not cleanly wiped, or if the buffer is not right sized, then information could be transferred that you didn't want transferred. So be very careful about using fixed length buffers when you don't know the length of the data. All right, the second version of 2D arrays is where we had the int pointer and we were doing new square brackets. So we call that dynamic because I didn't need to know at compile time the sizes that I was going to use. The pros are I can support triangular arrays or really any sort of ragged array that I want here. Every row, since it's declared independently, since it's allocated independently, it can have its own length. So if I wanted to use a very large matrix that was, symmetric along the diagonal, then in this way I could say, well, what if I just had each row was a little bit longer than the next row, and I could get myself into a triangular matrix and end up actually saving physically half of the memory. That'd be good. The other thing that's pretty cool about it is I can swap an entire row. So if I wanted to move a row because it's just a pointer to a row, I could swap a couple of pointers and easily swap rows. When I've got fixed arrays, since the memory is contiguous, in order to move one row into a place where another row is, I've got to get a temp row, copy everything out, move everything over, and then copy everything back in. So that is not nearly as fast. And of course, since it is dynamic, I can change the size at runtime. I can be doing something similar to pushback as I keep adding things to my dynamic C-style array, and then I run out of space. I can say, oh, wait, I'm going to go get some more memory, copy this into the new memory, and then start using that, which is fundamentally what the vector does in the STL. It just has been written by someone who was very good and had this tested, and it works out really well. The cons, every time I've got to do a new, I've got to do a delete. If I got to do a new square brackets, I got to do a delete square brackets. So memory isn't managed for me. I have to do this, and I have to be diligent about it. Otherwise, I can leak, I can cause crashes, bad things can happen. So that's not so great. And then because it's a to memory access, it's slightly slower. I've got to first dereference sort of my column vector, and that tells me, that my row vector, it tells me which row I'm in. Then I go to that location, dereference, and it gives me the entire row, so I have to figure out which column I'm in from there. So it's slower. We like to use the vector. It's cleaner, it's faster, it's easier, it's less prone to errors and mistakes. Speaking of errors and mistakes, one very common one is Offbyone errors. So we'll just look at some examples of them. I already spoke about what I like about for loops. I love a for loop that starts out with I equals 0, I is less than n, plus plus I. That's a for loop I can look at instantly and know what's going on. I don't have to worry about it. This first for loop we see here in line 5, I equals 0, but then j equals 0, but j less than or equal to size. I need to know, why are we doing a less than or equal to? This looks like I'm going to have a problem here, right? And it doesn't end up having a problem, because at one point it says, well, hey, when j is equal to 5, that's an okay thing. Let's write x square brackets 5. But you see here, x was declared with 5, so x is going to go from 0, 5 things, 1, 2, 3, 4. That's my last address. So square brackets 5 here is me accessing memory that I shouldn't access. So this is an Offbyone error because of the less than or equal to there. Be careful with those. This one is trying to copy values over, right? So we start out with k equals 0. That's good. K less than or equal to size. That's not so great. But the size minus 1 helps us stay safe, right? That's going to get me to that same number of things. That's done because we wanted to do a plus 1 here. So we thought if we offset that with a minus 1, it would be good. However, if you do the math, you can see at some point k can be 4, right? Because 4 is less than or equal to size minus 1. 5 minus 1 is 4. So k is 4 is okay. That's a good access here, but a bad access there. X is equal to, x square brackets 5 again is off by 1. So be careful of those. Here, this one, we've done something similar. We started now not at 0, but 1. So we're not trying to fill the first one, or maybe we are because we're doing this -1. But in the end, because this only goes up to size and starts at 1, this means this loop happens n-1 times, right? So all of x is not filled, one of them gets skipped. So be aware of those things. They can lead to bugs because occasionally, remember what a bug is, right? A bug is code that works sometimes, and then with the same input, it might not work another time, right? Most often people talk about bugs in office hours, they're really talking about errors. Like that was just written wrong. It doesn't work, that's not a bug. A bug is really hard to find because sometimes it works just fine. Other times with the same input, it might not work at all. So that's really what bugs are, and these are the sort of things that can lead to that because we might be sometimes writing into an area that the runtime complains about and could cause a crash. Other times we could be writing into the next variable in our stack frame, and occasionally we write a value in there that doesn't bother us as we look at the next variable. Occasionally when we overwrite an array though, and we write into the next variable, it causes problems because we changed information we didn't want changed. That's how bugs happen. Range-based for loops here. This is a great way to work your way through containers. We can use it with C-style arrays. We can also use range-based for loops with the STL containers. It works really nice. It is nothing more than new sugar, right? It's new syntactic sugar for for loops, right? Here's what a for loop is. We're pretty happy with that. I love this for loop. I equals 0, I less than 5, plus I. I know exactly what's going to happen there. This goes 5 times and tries to access everything that I want inside my array. So here I filled my array with the values 1 through 5, and this particular for loop is going to go through and double each one of them. So at times equals 2. By the time this one's done, my array is filled with 2, 4, 6, 8, 10. Now this range-based for loop below does the exact same thing. It's going to go into my array, and for each item in my array, it's going to give me sort of a temporary variable called item that I can use inside the loop. In this case, I look at the type of item. Item is an int reference. So changes that I make to item will actually fundamentally change the values inside my array. If I remove this ampersand here and I just have int item, that makes it a pass by value situation. So item gets assigned a copy of the next thing in my array, and any changes that I would make to item would not reflect in my array afterwards. But since I'm doing this with an ampersand there, then I know that item is actually have a real reference to something in my array, and this item times equals 2 is going to multiply these things there. So by the time I get done with line 10, now I'm looking at 4, 8, 12, 16, and 20. All right? You can choose whether to do this by value or reference depending on the application. If you're just using it for sort of a value that's going to be used to do other things inside the loop and not modified, it would be faster to run this with just an int, right? Because I do the copy there, but I don't have to dereference item every time that I use item. So be aware that you're using this and use it properly. Strings as arrays example. So strings are arrays. Really? Strings are arrays because really an array is just a pointer, and a string, C-style string, is just a pointer to beginning of where characters begin, to the place where characters begin. In a C-style string, we want to make sure we put a null terminator there. So here I've got this array, this fixed buffer, this fixed size buffer. You see name is declared to hold 20 characters. I've got this main that jumps in and tries to string copy from argv1 into name. What errors could occur here? There are a couple errors that are waiting to happen. The first of which is the easy one to see and could happen quite regularly. argv1. I don't even know if that's a thing, right? argc tells me how many things are there, And I'm always guaranteed to have argv0, which is the name of the program that I'm starting. argv1 is the first option or argument that's passed to the program. If the program is run with no options or arguments, then argv1 is not a thing. So as I try to stir copy from that, I'm asking for some pointer which I don't know what it's pointing at. That's going to cause a problem there. The other thing is I'm copying with stir copy. Stir copy is an old C style function. It takes the thing in this source pointer and writes all of those values to the destination pointer until it sees the null terminator in the source pointer, and then it stops. So if this has got 500 characters followed by a null terminator, it's going to try to write those 500 characters in this buffer of size 20. So we could have some segment problems there. How do we make this safer? Of course, let's use our C++ stuff, right? I'll get a C++ string, and then I can do my check to see if argv1 exists, right? argc has to be greater than 1 for argv1 to exist. Then if I just do this C++ style string, I can set that equal to a character pointer, and that's got an overloaded operator equals so that it actually does an allocation, make sure that I have enough memory in name, copies the value in there, null terminates it, and I've got a nice string there. So this is a much safer way to do this. I've avoided both of the errors that you can see in lines 1 through 4. Bugs gone. How about containers full of objects? Right? When we're creating objects in dynamic arrays in C++, we know that new is going to go allocate memory for us. If I say new object, then it's going to call the default constructor and create an object. If I say new square brackets to create a collection of objects, it's going to call the default constructor a bunch of times, once for each object in the array, right? So that works. If I don't have constructor types, like an int or a double, those things don't have constructors. They don't call a constructor there. They don't get initialized either if I use new square brackets. But if I do call new square brackets with an object, then the default constructors will be written. So always make sure in your default constructors that if you've got a constructor that you're writing, sorry, not just the default constructors, any constructor that you're writing, you want to make sure that every member variable gets initialized to something. Even if it's a default value, don't leave them out there if you say, well, I'm going to use this variable later. I don't need to use it now. I've seen so many errors in code by people not initializing a member during a constructor. So make sure you initialize with constructors. Delete, of course, if I've got a built-in type, it just makes the memory go away. But if I've got an object, it's going to call the destructor. If I call delete square brackets, it's going to call the destructor once on each object. So that code is important code as well. These container classes, as we look at them, are these things that we think of as objects. They contain multiple data items. I can put my own objects in there, or I can use built-in types. They're really nice because they give us sort of control over who gets to edit them. And you can think of that really importantly in a stack. If I put a thing into a stack, then I can't access it once other things are piled on top of it in the stack. So then the object, the container itself, is giving me sort of protection over it. It says you can't change the order of the way that things happened by grabbing something out of the middle of the stack. You have to use the stack interface. So that's the control and protection we're talking about. Also, container classes allow us to do some aggregate operations like copy or sort. We can do things like that pretty quickly with single commands or single calls rather than having to write loops. That's nice. And then once you start combining classes, which is what we're going to do as we move into this project 2, is combining containers. I put container within a container, a vector of vectors. We did some of that in P1. A deck of structs. So the struct isn't really a container, but a vector of vectors is a container within a container. That's really nice. Databases really are just a pile of containers. The database as you start the program, there's a container that has a bunch of separate databases in it. Then you select the database, there's a container there, and inside that database there are a bunch of tables. That's a container of tables, and you select a particular table, and that's a container of rows, and then you go inside that row, and that's a container of data items, one per column. And you look at other things in a database like indexes and things like that. Those are all containers, this fancy collection of containers. So working with containers is very common. Of course, we'll be using vectors, and we've looked at and used decks as well. Later on, we'll get to maps and unordered maps. We didn't really use stacks and queues directly because we used the deck in our particular application, but if you needed a stack or queue, you could probably use those with no problem. And then the one that we're going to avoid probably the most in 281, it's not the worst container ever, it's just a bad container during 281, is the list. That's the STL list there. That's really a doubly linked list, and we're just not going to use that in 281. It has its place. That place is not 281. So if you've got a problem, you think you're getting ready to solve it in 281, and you think, oh, I could use a linked list, go talk to someone, because you're thinking the wrong thing. All right, and then of course the STL is going to give us stuff. The standard template library. Standard template library. Most of the data structures in 281 are going to be containers. We look at them as ordered and sorted ranges. We'll talk about the distinction between ordered and sorted later. We'll be looking at heaps, hash tables, trees, and graphs. Today we're going to be looking at sort of array-based containers as an illustration. How can we implement these containers with an array-based sort of contiguous memory implementation? Every time we look at a container class, we've got some basic things that we want to do. We want to be able to construct and destruct them. Of course, usually it's not good to have a container if you can't put something in there. Most of the time when you put something in there, you also occasionally want to be able to remove them. Not all containers have remove as ability, but pretty common to have add and remove items, right? And if you put them in there and you can't get them out, it's not really that good either. So to retrieve an element is good. Getting these other things are sort of additional things that make things nice. So get the size, copy, assign an element. Those are sort of fundamental things to just about all container classes. You've got some version of these operations, and then different containers allow different operations or implement operations differently. So that's the question here. What other operations may be useful? And that kind of depends on the container. When we access container items, there's a couple of different ways we can do that. We can do that sequentially. You can see that here with this sort of chain of arrows. We bring in, we bounce, 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 right? In that case, when I'm doing sequential access, I need to find the nth item by starting at the beginning and then moving my way through. And that's kind of how linked lists work. Linked lists are sequential access only. This type of access is used in disks on computers. That's why it can sometimes be fairly slow. We're happy with SSD memory now. It's so much faster because we don't have to start at the beginning of a cylinder and work our way over to where the data sector that we want to read is. It's a lot faster. It's got random access. That's why SSD is great, right? You can find the nth item by starting at the base address, moving over n, and you get there in one step. So that's pretty nice. Random access, of course, doesn't mean it's doing things at random. It's still very deterministic. It's just that the user can choose at random where to go without having to step through there in a sequential fashion. This is how arrays are working. They use square brackets with random access. This is how main memory works, and now how SSDs work as well. You can get there really quick. Arrays can still be processed, of course, sequentially, because I can just square brackets my way for the first item, square brackets my way to the second item, a third item, and so on. So that's how iterators really function for us in the STL. We can use an iterator on a vector. So even though the vector has random access, I can square brackets inside of it. If I use an iterator in there, I'm going to be using sequential access to look at those things one at a time. So they've got some advantages and disadvantages depending on hardware, depending on speed, access, all kind of things that go in there. So this red question at the bottom is a great 281 question. What are the advantages and disadvantages? You need to be able to sort of expound upon those things when asked. Why would I like this one? Sometimes a linked list is going to be better. Why? Understanding that is going to make you really strong. Copying with pointers. So this one is a good illustration as to what's going on, or some of the way that the STL works. Right, so here you see I've got some source array and some destination array declared here in lines 2 and 3. And the goal here is to copy these 3, 5, 6, 1, these 4 numbers over to the destination array. Easy way to do that with no pointers would be to just write this for loop and square brackets access for write, square brackets access for read, put an assignment operator in the middle, copy happens. Another way to do this, much less attractive to our early stage programmers, looks like this. I can throw some pointers out there and then use pointer arithmetic and dereferencing, and boy does that look like it's a lot worse. In reality, it's going to be slightly faster, and it's got another benefit we'll talk about in a minute. So let's make sure we understand what's happening first. We get this pointer to doubles, and since an array is really just a pointer, I can assign this pointer to doubles to the source array. This pointer to doubles can also be pointed to the destination array. Those assignments are perfectly legal because they're the same type. Then my while loop says, as long as my source pointer is not equal to my source array plus size, right? And that's just like our zero-based indexing, right? So if I was to say I was going to look at 0, 1, 2, 3, and 4 in a container of size 5, that's great. I don't want to look at the one that's at 5. So it's that plus size that says once your source pointer is the base address plus the size, that's when you should stop. Everything before then is okay, but once you get to plus size, that's when you stop. So this while loop is just going to go through there and hit all size of these items and move them from the source pointer to the destination pointer. You see we're dereferencing source pointer. That's what this dereference source pointer gives us. Dereference source pointer and then set that equal to the dereference of destination pointer. So that says go to the source pointer, get the thing there, write the thing here, and then when we get done, we're going to move both of those pointers. Right? That's what the plus plus is. So now source pointer moves to the next data item, destination pointer moves to the next empty space. And that's how my copy happens. Now, why is this good? Why would you use pointers when the first code seems simpler? This is what the STL does when it deals with iterators. And you'll look at the functions in the STL, all of those algorithms, they don't work on containers, they work on ranges. And a range is something that's managed by iterators. And iterators are fancy pointers, right? An iterator allows us to dereference it, it allows us to compare it, and it allows us to either read or write from it depending on the type of iterator, right? So if you look in this particular set of code here, down in lines 10 and 11, you see here I'm comparing two pointers. I said that iterators can be compared. Here I'm dereferencing to write, here I'm dereferencing to read. So an iterator can also be dereferenced. And here I'm incrementing, in both of these cases, those pointers. And so since pointers and iterators can be dereferenced, can be compared, and they can be incremented, then it looks like I can use this code anywhere I can pass something into it that behaves in that way. So this is great because I can pass in an iterator to a deck, which can be dereferenced, compared, and incremented. And I can also pass in an iterator to a vector. So this exact same code would allow me to copy from deck to vector, or vector to vector, or vector to deck. And I could use the exact same code because as long as the thing that I'm passing into it, the things that I'm using to copy, these things respond like a pointer, as long as they can be dereferenced, incremented, and compared, then this code works. Whether it's going from linked list to vector, or deck to linked list, or deck to vector, or deck to deck, all the same code. So that's what's really good about the STL, is it limits the code that it has to write. So it limits the code that it can get wrong by using this generic programming technique. And this generic programming that I can achieve by using sort of these pointers. And so I can even use C-style pointer to vector or dec to C-style pointer, because a C-style pointer can also be dereferenced and so on. So as we're looking at containers, the two things that are important are, when I put something in there, what should I put in there? And when I try to get a value from out of there, how do I get it out? So our options are to put things in or remove them by value. I can do it by pointer, or I can do it by reference. So we're going to look at those three in comparison for both insertion and sort of accessing. The good news is, when I put the thing in there by value, the container is the thing that owns it and deletes it, right? It has to allow access to it, is responsible for destruction when it's done, and that's nice for me. The problem with that is large objects, of course, take a lot of time to copy. So just beware, that's a drawback, but it's not something that prevents us from using it, because that is actually the most common way to do things, is to put the object in there by value. If I put it in there by pointer, then I can certainly save some memory. I don't have to move large objects around. However, it ends up being unsafe because I've got a container full of pointers. Someone else has access to one of those pointers, and they may change or even delete what that pointer is pointing to. The container will not be notified. So it can be unsafe in the fact that as you stick pointers into a container, if someone else modifies what's at the other end of those pointers, the container doesn't know this, and then doesn't know that it shouldn't access a thing. So this can be used for character pointers storing data, but beware that it can be unsafe. Another thing that I might think of putting into a container would be references, which is another sort of fancy pointer thing that the compiler automatically dereferences for you. But since I can't assign to a reference, right? It has to be initialized that way. I can't, in the middle of a function, just assign to a reference, right? That makes it hard to put these things in there. So it's pretty impractical to stick a bunch of references inside a container. So that's why we don't do that too often. When we're going to check a value that's in there, how can I get it out? If I get an element, one way I could do it is I could do it by value, and that's okay. It's costly if I'm just sort of looking at, well, let me look at the thing on the top of this priority queue. It's a very large object. I just want to look at it. If that's returned to me as value, then it gets copied, and that takes time, right? If I say I'm going to send a pointer out of this thing, I've got the same problem with putting pointers into a container as I do with sending pointers out of a container. If I give a pointer to something in a container to someone else, they can overwrite the data at the end of that pointer, and now the container doesn't realize that the object that it's holding, because it gave its address away, has been modified, deleted, whatever. So that one isn't so great. It's unsafe. Another thing that happens often is if I've got a vector, for instance, and I got a pointer to some object in a vector, and somebody says, well, let's push back some more data into that vector. The pointer is to the address inside of the vector, right? But if the vector fills on a pushback and reallocates, picks up all the data it has, moves to a new location, new bigger digs, then the old pointer is still pointing to the place where it used to be, and that's now an invalid pointer. So beware, that could be unsafe. Usually, if we can get a reference out of there, this is a thing that behaves like a pointer, but it allows the compiler to make sure that that works out well. So we can use a sort of a reference into a vector. Even if that thing gets moved around, we can still keep track of that. So that's usually our good choice there, to use references. And you'll see how if I ask for top or front on the vector or deck, on the vector or deck, or if I look at front, if I look at back, if I look at those things in the stack and queue, those are going to be references. That's how the STL is going to do that. It's a good way to do it. Why do we have memory ownership? Well, let's keep our eyes on the data here. Here I've got an array A pointer that's pointing to this container of 5 items, And I've also got an array B, which is just a pointer, remember. They're declared as arrays, but they're really just pointers. So both of these pointers are pointing at the same data. That's great. If I modify A, then B's changes are similar because B's pointing at the same data. And sometimes this is a behavior that you want. Very rarely, however, though, because it's strange to have some collection of data and want to be able to write to it here and read it somewhere else. It can happen, but you have to be careful that you create those two pointers differently, because one of those can be deleted at the end of the day and the other one can't be deleted. Because if I delete what's at array A and then later try to delete what's at array B and they were pointing at the same thing, then I get a double delete and I've got a memory error and bad things happen. So be aware that when I want to have memory like this, if I've got an object that's got this array in it, I would want to have each object have its own copy of the array, so that when the object gets deleted, then it can free up its own memory without taking memory from some other object. So beware when we're doing copy construction and assignment, if I've got my own object and I create a duplicate object, what happens is, without writing my own copy constructor, I'm going to get a default copy constructor, and all that does is a member-wise copy. Value A holds the same thing as value B does, and whether those are integers or doubles or pointers, there's no difference. So in the case where this object has some data in there, and a pointer to a location, if I copy this object, it's going to get a full copy of this here, full copy of that there, and an exact copy of this, so it ends up looking like that, which is our slide previous to this. So beware that if the default constructor is used and I've got my own dynamic memory, then I'm going to have problems because I won't be doing deep copies. How do we get around this? The easy way is to make sure that each object is owned by one container. Then when that object gets freed, no other container can be affected. Another way to do this is with reference counting. In this case, you don't really have ownership. The operating system, as it allocates things, it says, here's a chunk of memory, and because it was just freshly allocated, I'm going to say, as you assign a pointer to the beginning of this address, the beginning address of this memory, then I'm going to put a reference count on there and say, one thing is pointing at this memory. If I set something else equal to it, I can say two things are pointing to this memory. Three things are pointing to this memory, and so on. And every time something goes out of scope, then I'll say, well, it's no longer pointing to this memory, so we're going to subtract from that reference count. And eventually, we'll get to a situation where nothing is referencing memory, so the reference count on a memory allocation is 0. Then I need some garbage collection, right? Garbage collection happens in languages like Java, where or even in C++, where smart pointers are used. When a reference count goes to 0, then it's okay for that memory to be deleted. So this is a little bit slower because we've got to have a garbage collector around there, something that's sort of watching memory reference counts and say, when this goes to 0, then we'll go deallocate it. Because once it's gone to 0, no one can possibly access that memory anymore. As long as the reference count is above 0, then someone can access it, and that memory should probably stay around. So that's the second idea, and can be used in some languages, C++ included. When pointers have ownership there, now we're being careful here, right? When an object is owned by another container, it might be prevented access. Other items might be prevented that access, which is great for privacy. It's great for safety, right? We have to be careful that when we delete some chunk of memory, that we don't delete it twice. This could crash the program. And every time that I've got some declaration there, a constructor that's got an allocation, and I want to make sure that there's a matching destructor to deallocate that memory. If I don't, I can cause memory leaks. So one safety tip here, this defensive programming thing, is instead of just deleting some pointer that I've newed or whatever, I want to make sure that as I delete the thing, I go ahead and set that equal to null pointer. What that does is it prevents some other reference to this pointer, like maybe I had also set something equal to pointer previously. Delete pointer frees up the memory, but anything else that was already pointing to pointer is still pointing at that same memory. And more importantly, delete doesn't clean the memory, it just removes the reference to the memory. So the data is still there. So this can lead us to buggy behavior. If I've got a pointer into memory that's been freed, if I access that pointer, I can still look at the data that was there as long as nothing else has gone to write in that location. So sometimes what was there is still there and it works. Other times something comes in and writes in that location and it doesn't work, and there's my bug. So the good way to do that is to delete this pointer and then set pointer equal to null pointer. So then anything else that's accessing that gets null pointer as its value. So this is going to give you a good solid crash when you I'm having trouble today here. When you try to access a pointer and it's set to null pointer, then you'll get a solid crash. Whereas if you're accessing a pointer that's invalid, right, and you try to dereference it, it's going to work. You're just going to get memory that you might not know what's there, right? So if we set this pointer equal to null pointer, then we won't ever try to dereference what's there, right? Another thing I can do is if I delete it, try to delete a null pointer, delete of null pointer doesn't cause a problem there. So this also prevents double delete errors, and that's nice. What about memory leaks? Memory leaks are a problem, right? You've allocated some memory and then you've lost a reference to it. So the operating system doesn't know the memory is no longer available, and your program has no access to it, so it can't use the memory. If it needs memory again, it's going to have to go get new memory. So once you start leaking memory, the overall memory in the computer is being used up is being made unavailable, even though programs might still need to use memory. And so this can be a problem. At the end of any program, obviously the operating system is going to go ahead and deallocate the memory that running program used. So those memory leaks can kind of get cleaned up by the operating system. But the problem happens more in that situation while it's running, right? If a program is leaking, this is pretty classic in Windows 3.1. Back in the old days, you would use a Windows machine, and if you were full-time using your Windows machine in office, just working during the day, Excelling, Outlooking, doing your mail, whatnot, because those programs were leaky, or other programs were using dynamic link libraries and would leak memory 2 or 3 times a day, you would just have to reboot your computer because so much memory had been leaked that the machine would slow down and slow down, because every time it went to go get new memory, it would have a hard time finding memory because there was leaked memory that other programs were thinking was in use but weren't using. And so that's where memory leaks can be bad. Your code should be reusable in a larger system. So even if your code is leaking a little bit of memory and somebody says, well, I want to run this program 100 times because I'm doing final grading or something like that. Well, if it leaks a little bit and then it gets used multiple times, that's still going to lead to a situation where it might run out of stack/heap memory and then cause crashes. So be careful there about memory leaks. The autograder does look for memory leaks and does this by running Valgrind on a few test cases. So if you see you're getting memory leak points, you should usually get them in these projects. P2 is where we can really get to doing our own memory allocation, so we might have some problems there. But projects 1, 3, and 4, if you're just using STL containers, you shouldn't have memory leak problems. Oftentimes, however, people don't get memory leak points on their projects because there are certain tests in every project that you have to pass before memory leak checking works. So if that project you don't pass that test, it won't run memory leak checking and you won't get those points, right? So just be aware that if you see that you're not getting those points and you're thinking, well, I didn't do any news or deletes, I don't even have anything but vectors and decks and things like that, I shouldn't have memory leaks, it's not my fault. You're right, it's not your fault, it's just that the autograder isn't keeping track of that. So if you want to check for memory leaks, though, be sure to Valgrind everything. Even if you've got something that works and you don't know if there's memory leaks, Valgrind is a great idea, right? If you've got something that's going wrong, you got something that's going right, I would always run Valgrind to make sure that I'm not doing something wrong. A lot of times, code that works all the time, sometimes you can still find errors in it because some bad decision was being made based on memory that wasn't initialized or things like that. So make sure you run Valgrind a lot, especially when you're coming to office hours saying you have a problem with your code. Usually we're going to ask a few questions like, what happened with Valgrind? Or if you're talking about performance, what did the perf report say? We've got these tools. You need to use your tools. Learn how to use your tools. So the next part of this lecture, we're going to be working on this capital A array class. And this is just a simple implementation of square brackets arrays, but we're going to add our own bounds checking. You can see what the overhead with that to do that would be. And just implementing it's pretty interesting here. You'll get a chance to see some code and work through it as well. So I've got this class, and the class has two private members. It's got a pointer, to this case, doubles. So this array only holds doubles. If you wanted to write this with something else, you could write this templated, or you might write another one that holds integers or whatever you wanted to do. So in this case, it's got a pointer to my data, and then it's also got that length, which is what we said. Anytime we've got a C-style array, we need to keep the length somewhere. So I've got this pointer to data, and in this is called static initialization here. I'm setting these members equal to something. And this works as well as the constructor. This is going to set my length to 0 and my data equal to null pointer for every one of these that I create right away. So in this case, I don't necessarily need to write a default constructor. This works as the default constructor. I do, however, have a constructor. In line 6 there, you see I've got a custom constructor that takes a length. This length then is going to be used to assign the value of my member length, and then I'm going to initialize data as a new square brackets collection of doubles, length, length. Very important, this initialization list takes place between the colon and the curly braces of the function, right? That's where the initialization list, and these things are comma separated. You have to do them in the order that they're declared. So you see in line 2, I declared length. In line 3, I declared data. So my initialization list in line 6 has to have length before data. The compiler will complain, and it's a somewhat cryptic message that doesn't really clarify the fact that you did them in the wrong order. So if I had tried to initialize data first and done a new square brackets double len and then set length equal to len, I would have a problem there. Now, I don't have to put everything in the initialization list that I have as member variables, but if I can put them in the initialization list, I would like to, because it happens before or while the object is being created, as opposed to after the object has been created, and it does things. So if I was to set, for instance, data equal to something inside of the curly braces, right? If I was to set data equal to something in here, then I would first get data, the first pointer, and then I would be assigning data to a second pointer here. So that is why we like to use initialization lists when possible. There's my custom constructor. It does allocation. I've got to have a destructor. Line 8 is that destructor. Function, no return type. Function name, same as the class name. That's how I know it's a constructor or a destructor. If it's got the tilde in front of it, that's making it a destructor. Without the tilde, it's a constructor here. So this is my destructor. I'm going to go ahead and delete square brackets on data and set data equal to null pointer to keep that nice and protected, right? And finally, I've got this getter. Just give me the size of this thing. It's going to return size t as a const. This is a const function, meaning when size is called, there's no way that this object will be modified. So there's about 5 different places where you can use the const keyword. It's probably one of the more complicated things in C++, the language. You can put it a bunch of different places. Here, the const, after the function name, after the function parameters, before the curly brace, says that this function will not be modifying the object that it's called on. So whenever I use some array.size, the compiler knows that that .size function will not change the object. And this helps the compiler do other things with pipelining and speeds things up. When we can use const functions, it's a great idea to do it. So this is going to return length, and it returns it as a value there. So that's good. There's my setup. As we work through this, I got this question I get all the time. Should I use this as a class or a struct? In the end, it doesn't matter. Class and struct generate the exact same executable when put through the compiler. The only difference is classes have members that are default private and structs have members that are default public. You can add a public or private tags, right, to anything. So I can say this class has public members. I could also say I've got a struct that has private members. It's just the default way things happen. So with struct, they're public by default. With class, they're private by default. Other than that, they compile to the exact same thing. So I always have this sort of inner wrestle when I'm writing code with structs and classes, because I was old school and I learned structs before classes came around. And then when classes first arrived, structs couldn't contain functions. So a struct could only be data, and a class could be an object, because a class could have both data and methods. So now I always feel like if I'm going to do something that's just sort of a data-based thing, I'm going to put that in a struct. I wish I would always write them as classes, but I still sort of think of them when it's really simple. I write it as a struct, and then I don't have to do the public thing. So I don't know. It's something that you got to get used to and learn how to use. But know that it's not something that you should stress about. You shouldn't stress about it. You just make sure that you get the access that you want. If you want to have access to it outside the object, make it public. Whether that means putting the whole thing in a struct, or that means putting part of it into a class and making that part public, is up to you. Try to make your code clean and clear and as readable as possible. Here's my copy constructor. And this is a deep copy because, remember, each one of these arrays has a pointer named data to its own allocated new square brackets memory, right? So if I'm going to do a copy constructor, and I can tell this is a constructor right away because the function has no return type, and the name of the function is the name of the class, right? And I call it a copy constructor when I'm passing in a const reference to one of those objects. And so this is the copy constructor when I make one from an existing value, or if I try to initialize one with an assignment, I'm going to get the copy constructor called there. So here you see I'm going to do the same sort of thing. I've got my initialization list. I'm setting the length of this new one, and I'm setting the data of the new one as well. In this case, I want to make sure the length is the same length as the one that's passed in, A's length here, and I want to make sure that data has the same amount of space as A has as well. So I can set that to a new square brackets double on that length. Then my initialization is done. I'm going to go through after that and do the actual copy, which is what you see here in the for loop in lines 4 and 5. It's just going to go through there and get that taken care of for you. All right, so that's my deep copy, right? Because if A has its own data, now after this construction, the new value that the new variable of type array that I'm declaring will also have its own data array copy there, right? This copy constructor lets me do these things here like line 7. Well, the copy constructor doesn't give me line 7, right? Line 7 gets from the custom constructor on the previous page. Give me an array of size 10 and put that in A. Give me an array of size 20, put that in B. Line 9 is a copy constructor, right? That's saying give me array C and initialize that from B, right? Line 10, although it looks like an assignment, array D is equal to B, because that's happening at declaration time, that just turns into syntactic sugar, right? It looks like an assignment. You're setting D equal to B. The compiler, however, is declaring a variable. So it says, if I'm declaring a variable, I'm not going to create one and then overwrite it with some other value. Why wouldn't I just copy construct D from B? So that line 10 there looks like assignment. Because it's at declaration time, however, it is going to be a copy constructor call there. In line 11, when I do that, now that's an assignment. I am not going to get I'm not going to get a deep copy here because I haven't written an operator equals. So I'm just going to get a member-wise copy. Length is going to be set to the other things. A's length is equal to C's length, and A's data is equal to actually pointing to the same data that C is pointing to. So without a custom operator equals, I'm going to have problems here because I don't get a deep copy. In terms of complexity of this is pretty straightforward. you can see that the only thing that matters inside this function in lines 4 and 5 is the loop, right? And that loop is an n-based loop. It's n where n is equal to length. I can see the things in the initialization list, setting length equal to a length, that's an assignment, one step. Allocating a chunk of memory, that's one step as well. So I've got this n-based loop with a constant amount of work inside of it. So this is a constant, sorry, this is an n-based operation. So this is linear in n. If I looked at this, best case n, worst case n, average case n, it's always n. All right, how about this copying thing? Say, well, copying and assignment do basically the same thing. So if I wanted to write an operator equals, I could sort of abstract the copy code here, and then I could use the copy code while doing a copy constructor. I could also use the copy code while doing operator equals, and I could save code that way by writing it once and using it twice. It's a great way to do this. However, in order for me to use operator equals, I want to make sure that I don't kibosh myself, right? So, for instance, an expression like set a equal to a, if you wrote that in your code, it would be a little silly, but you would expect when you got done with that line that a would be equal to what it was when it started. However, if I start out and say, well, when I do this assignment, I want to jump into this copy from here. And because A already has some data, I want to delete the data that it's pointing at. So when I create some new one from the incoming other, then I'm in good shape. But if other and this are the same, like as in A is equal to A, right? Here's this. This is other. So if I'm setting this and other equal to itself, the first thing I do is delete data. Now I've deleted both of their data because this and other are the same thing. So to prevent this from being a problem, we end up with this idiot check here, lines 16 and 17. If this is not equal to other, if I'm not assigning A equal to A, I have to make sure that they're two distinct objects before I do copy from. Because if I'm using the same object, then obviously I don't want to do anything. So we call this an idiot check because only idiots set A equal to A. We don't need to do that too often. All right? But because it might happen and you wouldn't want A equal to A to break anything, you have to add this idiot check. So then everyone who's doing an assignment has to do this additional work. Let me check to make sure that some idiot isn't setting A equal to A. Because I'm obviously not an idiot. I wouldn't set A equal to A. But I have to check to make sure somebody else doesn't ruin this. So that's the way that we can sort of save some code. An even better way to do this, however, is to use what's known as the copy swap method. And the copy swap method, what that does is it's going to make a copy and then swap the data members between that copy during the assignment. So to make this happen, we're going to go back to our previous copy constructor as it was. So all of the copy work happens in the copy constructor, right? We see no copy work inside of operator equals, right? I mean, the copy work of setting an element equal to some other element. That's all happening inside of the copy constructor, right? So the first line inside the copy swap operator equals is make a temporary copy of other, right? Now temp is a local variable inside operator equals that has a full deep copy of other, right? So if I look at this, the way that I might think of this as happening is here comes other, and I'm trying to set that equal to A, for instance, right? So you can imagine A might have something like its own length and its data, which is a pointer off to some stuff, right? That's what other has. And A has its own length with its own data pointer off to some other stuff. Great. Now, when I make this copy of other, I say set temp equal to a full copy of other. So there's other, there's A. So temp is going to have a full copy of the length of other, and it's going to have its own data pointer off to its own copy of these things right here. All right, so now I've got that. That's that's line 11. Then I do a swap. And what the swap does is it changes members here, right? It changes A's length with temp's length, right? Because A is my sort of this, right? You can think of this and A being the same thing. And then when I swap these pointers like that, it's great, right? So that swap really makes D from this point here, while D from temp points there. All right, that's great. Now I just return a pointer to this, which is give me back this value. And you see that because temp had a copy of others' data, now A has a copy of others' data. But what's also very cool about this is temp is going out of scope. It's going to have its destructor called. And right now, temp data pointer is pointing at this is old data. So when temp goes out of scope, it calls its destructor and cleans up this or A's old data. And in this way, we don't have to worry about doing the cleanup ourselves. We don't have to do the delete ourselves, which means we don't have to do the protection for the delete. We don't have to make sure that we shouldn't be deleting this thing we're about to delete. And so this removes the idiot check. Now, idiots that still do things like A equal to A, they pay the full price because they make a full copy of A, then they delete a full copy of A just to end up with the original copy of A. So this version helps out people that don't do dumb things and punishes people that do dumb things even more. So, moral of that story, I'm going to go with don't do dumb things. All right. So that's the copy swap method. You can implement that whenever you're doing your own operator equals and you've got some dynamic memory involved. There's my example slide. I already did the example. So we end up then with, of course, the big three that we already had to implement when you've got dynamic memory in your class. If you've got dynamic memory, you've got to have a constructor to make that happen. You've got to have a destructor to make that happen. You got to have a copy constructor to make sure that the deep happens. And you have to have an overloaded operator equals so that deep assignments can happen as well, deep copy assignments. So those are the three that we always have to implement. Since C++11, we've got a couple more optimizations, which is copy constructor from R value, overloaded operator equals from R value. We're not going to talk about that in 281, but the brief on that is when the compiler knows, for instance, an object is getting ready to go out of scope, if you want to say, I would like to return a vector from this function. Well, the vector was going out of scope in the called function, and since we can do overloaded operator equals from R value, rather than destructing the value, what C++11 would do is like, if this is going to go out of scope, I won't destruct it. I'll just use that instead of making a full copy of it. So that can speed things up pretty nicely. So like I said, we're not going to talk about it. If you see something, though, where it looks like ampersand, ampersand, you're like, I understand what reference variables are, but what are double reference variables? That's working on R value stuff. So not something we cover in 281, but something you should understand. Something would be helpful to understand. Certainly as you go into interview season, make sure you understand what R value versus L value is. Look it up. Wikipedia is your friend. All right, I'm going to try to wrap this up in the next few minutes. I always go a little over. I talk too much. Array class is not really any good without square brackets. I mean, that's one of the things we love about the array is we got this nice syntactic sugar here. If I wanted to do my own pointer arithmetic, I would just use pointers. So I'm going to try to add square brackets functionality to this, right? And that's done by adding an operator square brackets. And you can see this operator square brackets overloaded function here. So now I'm saying I'm going to return a reference to double with this square brackets. And this is a non-const version because I don't have a const here. If I wanted this to be const, I can insert a const there and I could insert a const there. Right? The const here says that this call will not in any way change the container. Right? The const here says what you get back cannot be changed. So this one is non-const, It just says, what am I going to do here? This is the reason why I wrote this class, is to put some bounds checking in there. So if I ask for some I that's off the end, this check right here is going to say if I is less than length, it's a valid square brackets. Just return data at I. That's good. If, however, I is greater than or equal to length, I shouldn't be able to dereference that. So here's where I'm going to throw the runtime error. And you can see why we don't have this check. You imagine that every single array access had the, hey, if this was in bounds, then we can do it. That would slow us down if every single array address access had a bounds check. So C++ keeps this slow thing off of there and just lets you read or write from wherever you want to. Hopefully you stay in bounds, right? It's like C++ is a gun that allows you to shoot yourself in the foot. That's right. All right, so this version is the const version. You can tell by the body of the code, it's identical. So there's nothing different here. The const declaration, though, helps the compiler separate things. And so when we've got const version, like I mentioned, this const says the calling of this function will in no way change the array operator, the array object that we're calling it on. And this const says the value that gets returned from that array cannot be modified. All right, two separate things there. Why do we need two versions? Well, sometimes const things are used in places where we don't think that they're used. When we're doing something like the stream insertion operator, right? Stream insertion operator isn't expecting to modify an object, so it's generally called with a const reference to the thing that it's being called on. So if I give a const reference to an object and then try to call a non-const function within that object, I'm going to have compiler issues. So I need both of them. You can see here some example. Square brackets 0, I'm writing to there. Clearly this is not the const version because I'm going to be changing this value. Square brackets 1, I'm changing this value as well, right? So both of those need to definitely have the non-const version here. This one I need to have non-const version in line 4 here, at least for square brackets 2, right? These two could be implemented either way. I could use them const or non-const, but if I was going to do it const and I didn't want to change them, then I would need the const function to do that. So you would like for these to be done with with const versions, because we're not making changes as we're reading what's at address, what's at index 1 or what's at index 0. So here's an example of how a function, this is a helper function that someone wrote to say, I want to just be able to take my array and feed it to an output stream, right? I'm going to overload the stream insertion operator. So when I do that, I can just run through this and square brackets access these things and ship them out. But if I don't have my const version of this, because see, I'm passing in this array class R, I'm passing it in as a const value. If I don't have a const version of square brackets, this is not going to compile. Because if this is a non-const function here, I'm trying to call a non-const function on a const object, it's going to not happen, right? Not going to happen. You don't have to worry about which one to use either. Once they're created, the compiler knows which ones it wants to use. So as long as you've provided them, the compiler is going to choose appropriately, and this allows the compiler to optimize things for speed. Pipelining decisions that are made to say, well, I know this object isn't going to be changed, so it can be used in a faster way in terms of the way the caching and pipeline works. So don't worry too much about that either. It's beyond the scope of 281. Just know that when you can make things const and use them as const, it will speed things up whenever possible. It will never go slower to use a const version, but it could possibly go faster. All right, how about insertion? So here's just overriding insertion. This is just a simple example, one that should make good sense, right? First thing I wanted to do is make sure that I'm not trying to insert something off the end. The whole goal of this was to have bounds checking. There it is, lines 2 and 3. Line 4, a not so favorite for loop. I mean, it's necessary, but this is a decrement for loop. You have to figure out, where am I starting? Where do I stop? I is greater than index minus I. So this is a reverse for loop. Not the worst thing in the world. It's just, in this case, important, because if I was going to do a plus plus and I was trying to insert something, it makes it more difficult as I try to insert something. So here in this particular instance, we're trying to insert a value here at index 2, right? This example is saying insert the value 3.4 here at index 2. If I was trying to use a plus plus, then I would have to sort of like, let's write 4.2 over here so that I can write 3.4 in there. And then I'm going to use 4.2 later. It needs to go back there, but 5.9 is there. So let's write 5.9 here. Then I can write 4.2 there. Now in order to put the 7.3 out of the way, then I can put 5.9 there. And now I can move 7.3 in here. So I end up doing a lot more writes if I'm sort of pushing my way from left to right. That's how the plus plus I would work. If I'm decrementing, however, if I decrement and start my way from the left, what I'm saying is I can, instead of moving, I can just overwrite. So in this case, I say, I know that, oh, Siri's getting back up, Siri. All right, there we go. So with overwriting, I can say, well, I always am going to write the 7.3 there. I can write the 5.9 there, the 4.2 there, and I've got 2 copies of 4.2 now. But then as I write the 3.4 in here, you see I end up with the desired effect here, and that's what this minus minus loop is doing. That's why I'm going from the right side to do my insert instead of going from the left side to do my insert. Red question here, are arrays desirable when many insertions are needed? Hopefully you're thinking, no, they're not. Got to do a lot of insertions. I'm going to be moving a lot of data. As I look at the complexity analysis on this, say best case, I'm inserting after existing data. I can do that in a constant amount of time. Worst case, I'm inserting at the very beginning. So I've got to move all n of the items, or at least n minus 1 of them as I'm inserting things in there. So all my data gets shifted. That's worst case. On the average case, though, I would end up with n over 2 things being moved. Sometimes it's less, sometimes it's more. Sometimes it's almost all of them, sometimes it's almost none of them. But if I were to take sort of like 50 insertions at an average location and then divide that total number by 50, I would end up with something that would look like n over 2. So my big O then ends up being a big O of n, because remember, n over 2 is just n times some constant. Right? So there we go. This complexity of insertion then is big O of n in the average case. Wrapping things up, we got study questions here. Use these as you're working your way through this. Another thing that I think is very important, as you're trying to make sure that you understood this lecture is not that challenging. You should say, yeah, I understood all of this stuff, but that's not really good enough. In the end, you want to be able to show that you understood this stuff. So during your studying, during your lecture recap, during your review of the material, think, how might test questions be asked of me to show that I understand these containers, right? How might questions be asking me to show that I understand memory ownership, or what are disadvantages of arrays? If these questions are easily answered by you, then it's not a great study tool. If you can say, I can easily answer them and think of ways that they might be asked of me, then that makes this a great study tool. So make sure that you can cover these things as well. Go back. I strongly suggest you type this code in. The more code that you have, the more code you've done and debugged, add some more functionality to it. Add an append function. Add, at this point, because the size of the capital A array class is fixed at construction time, you can't make a dynamic. Make a dynamic version of it. See if you can add a pushback function to this. See if you can add resize, reserve. It's a great way to work on things, is to take something that works and extend it. Have a good day.